Welcome everyone to the November Kraw lecture. I'm George Kraw, and here next to me, virtually and physically, is Rafe Shannon Kraw.
Hi everyone.
This lecture series features acclaimed UC Santa Cruz scientists and technologists who are grappling with some of the biggest questions of our time. Tonight, we turn our focus to the pressing issue of climate change. UC Santa Cruz continues to lead the way in climate change research, and tonight, distinguished Professor James Zachos shows us how we can learn about our future by looking at our past. Moderating tonight's discussion is Christina Ravelo, Distinguished Professor of Ocean Sciences and Associate Dean of Diversity, Inclusion, and Equity at UC Santa Cruz. Professor Ravelo's research focuses on determining the role of ocean processes in past climate variability, including investigation of climate transitions, warm climate processes, and regional expressions of global climate change. She has held leadership roles at the National Research Council, National Science Foundation, panels the American Geophysical Union, and the International Ocean Discovery Program. She is also a fellow of the California Academy of Sciences. Before we begin, I'd like to share a few details about the event tonight. We are using a webinar tool, so there is no chat function. We will have an opportunity to answer your questions at the end of the program, and we invite you to submit your questions into the Q&A box at any time. Tonight's event will be recorded and available later on YouTube. Now I'll turn this over to Christina.
Hello, everybody. Thanks, George. So it's my pleasure to introduce Jim Zachos. Jim is a distinguished professor of Earth and Planetary Sciences and the Ida Benson Lynn Chair of Ocean Health at UC Santa Cruz. So his research interests encompass a wide range of problems, including the interaction between biogeochemistry, climate, and ocean evolution in past time periods, with particular emphasis on understanding how the Earth operates during warm periods, present and past. So for example, greenhouse gas forcing in the present and past certainly has a well-known global warming effect, but the feedbacks that might amplify or ameliorate that warming effect are difficult to quantify, and thus are a main focus of the climate change research community, including the work that Jim does. In addition, the regional expression of warming is perhaps the most relevant to our daily lives. So you'll see from his talk that Jim is attacking this question by looking at the factors that drive the hydrological cycle, which in large part determines which places get drier, which places get wetter, which places experience changes in variability kind of in the face of global warming. So before I let Jim talk, I want to highlight that Jim has been at UC Santa Cruz for over 25 years and has been the primary leader in the establishment of UC Santa Cruz as a center of excellence in paleoceanography and paleoclimatology. Certainly, my career would not be what it is today without Jim's spirit of collegiality and generosity and his passion for intellectual exchange. He also has had a tremendous impact on his discipline nationally and internationally, and for that, he has received many awards and accolades, including being named a fellow of the American Geophysical Union, a fellow of AAAS, and the California Academy of Sciences, as well as the recipient of many national and international awards, and in 2017 was elected to the National Academy of Sciences. So before one more thing before I invite Jim to begin, I just want to reiterate what George said, which is that please use the Q&A Zoom tool to ask questions as you think of them. And there will be a question and answer session at the end of the talk, and I'm sure Jim will be very happy to discuss your thoughts with you. So I will now turn it over to Jim.
Okay, thank you for that very kind introduction, Christina. And I can also say that I've benefited from your presence here over the years. So thank you. And And George Kraw, thank you for your generosity in supporting this important lecture series. I've actually learned quite a bit from attending some of these lectures. Okay, I am sharing my screen and I'm about to launch PowerPoint. And I assume everyone can see this okay. So my lecture today is going to focus on Earth's past climate, mainly the last 66 million years. And then I'm going to also focus on one very special event that occurred about 56 million years ago, a global warming event. And I'm going to talk about what drove these changes and the implications for future climate change. But before going into the past, I'd like to spend about 10 or 15 minutes sort of reviewing our understanding of present day climate and how climate might change in the future. And I think this is useful for people who are certainly novices to climate change, but even for people who have some experience. And so please bear with me as I sort of slowly jump into this topic. Now, some of you might be wondering why this image of Earth taken from the moon. And the point of this is simple, that both the Earth and moon receive the same amount of solar radiation. And that solar radiation is what warms the Earth and the moon. However, the temperature of the moon is on average lower than that of Earth, and it's much more variable, swinging by hundreds of degrees from day to day and over the course of a year. And of course, the main reason for the differences in the temperature of the Earth and the moon is simple, that the Earth has an atmosphere. It has a greenhouse atmosphere. That atmosphere contains water vapor, and it contains carbon dioxide. And really, those are the two main greenhouse gases. A lot of people think that only water vapor is important for maintaining the climate of the Earth. However, the problem with that is that water condenses at relatively high temperatures, let's say 0 degrees centigrade. And given the Earth-Sun distance, the amount of solar energy that the Earth receives from the sun, with just water vapor, the Earth would pretty much freeze to an ice ball. And this has been verified with numerical models. And so the key is carbon dioxide. Carbon dioxide will not condense at the same temperatures as water. At very low temperatures, carbon dioxide will remain as a gas. And so it provides the lever, one of the main levers for the greenhouse effect, because in some ways it controls the amount of water vapor that's in the atmosphere. Okay, that's not a disputed fact. It is a fact that all climate scientists agree to. Now, let's take a look at what global temperature is doing. This is a plot of based on measurements or observations coming from 1880 to the present. And it shows the variations in temperature by hemisphere, northern in red, the southern hemisphere in blue. And you can see that over the last 100 years or so, the temperature has been rising. It's been accelerating certainly over the last 40 years. And one of the differences you notice between the northern hemisphere and the southern hemisphere is important in the sense that the southern hemisphere is warming a bit more slowly than the northern hemisphere, simply because of the differences in the distribution of ocean versus land. There's much more ocean in the southern hemisphere relative to the northern hemisphere. And the ocean takes longer to heat up. And so we can actually see a disparity at the rate of heating between the northern and the southern hemisphere. So those are direct observations. The question is why, and we understand this quite well, which is that the concentration of carbon dioxide in the atmosphere has been rising. We know this from direct measurements over the last 60 years or so, mainly taken at Mauna Loa Observatory, but other locations around the world. And then prior to the time that we started collecting samples of the atmosphere, we can get the concentration of CO2 in the atmosphere using a geologic archive. In this case, ice cores, bubbles trapped within ice cores that are accumulating through time, either on the Antarctic ice sheet or on the Greenland ice sheet. Those bubbles trap the air at the time the ice forms. And so by simply measuring the concentration of CO2 in those bubbles, we can reconstruct the concentration or the chemical composition of the atmosphere going back in time. And this is just an illustration going back 1,000 years, showing that CO2 levels have been roughly around 280 ppm for most of that time, and only started rising around 1860. Now we have other CO2 data that go further back in time, which we'll look at a little bit later. The question is, why the rise in CO2 at 1860? I think we understand this quite well. This was around the time that the steam engine was invented and put into widespread use. To drive steam engines, we basically burned, well, wood and coal, mostly coal. And so carbon emissions started to increase from the combustion of that coal. Eventually, we started burning oil and gas with the invention of the automobile. And so to the present day, you can see the relative contributions of these different fossil fuel sources to the carbon emissions, which are around 12 gigatons of carbon per year. A gigaton is about 1 billion tons. And so this is the number for just carbon, 12 gigatons of carbon per year. And you can see that this has been rising fairly steadily for the last several decades. Okay, now a question that I often get, and probably other climate scientists, is how do we know that the carbon that's accumulating in the atmosphere over the last 150 years is from the combustion of fossil fuel? Well, as it turns out, there are multiple ways that we know this, but one of them, which is really important, and you'll see the relevance of it as we go back in time, has to do with the chemical fingerprint. And this is the ratio of carbon-13 to carbon-12 in the CO2. Now, you might recall from high school chemistry that the atomic mass of carbon is 12, reflects the fact that it has 6 protons and 6 neutrons in the nucleus. But 1 out of every, say 100 carbon atoms has an additional neutron in the nucleus. And so the mass is 13. So there's a slight mass differences between these atoms or these isotopes of carbon. And the reason why that's important is because it affects the way that these carbon isotopes are in effect taken into, say, organic matter. They get fractionated slightly because of the differences in mass. Now, we can easily measure the ratio of C13 to C12 in any material, convert it to CO2 and introduce it to a mass spectrometer. We do this upstairs in the labs here at UCSC. And then what we typically do is report the ratio of C13 to C12 of our sample relative to a universal standard. We -1 times 1,000, and we refer to this as delta C13. So if the ratio of C13 to C12 of our sample is higher than the standard, you get a positive value. If it's lower, you get a negative value. So an interesting aspect of the C13 to C12 distribution in carbon-bearing materials is in organic matter. All organic matter has a C13 to C12 ratio that's relatively low. As organic matter is being composed or synthesized, there's a preferential uptake of carbon-12 over carbon-13. This has something to do with the strength of bonds that are being formed and broken during this synthesis process. So the delta C13 of biomass is roughly -25 per mil. Biomass gets buried and compressed, and with time is converted to oil, gas, coal, fossil fuels. And then eventually that oil, gas, coal is extracted and we burn it for energy, emitting CO2. And as it turns out, that ratio of C13 to C12 of that carbon being emitted from cars or smokestacks is the same as the original biomass, minus 25 per mil. So it turns out, if you go back to, say, the ice cores, and where we've measured the concentration of CO2, shown here in black, over the last 1,000 years, and you have this rise in CO2 starting at 1860, we can take that same carbon dioxide from the ice cores and measure the ratio of C13 to C12. And when we do that, what we find is that the C13 to C12 ratio of atmospheric carbon dioxide started to decrease rapidly at the same time that the concentrations in the atmosphere started to increase. And this is a clear signal of a very isotopically depleted carbon being added to the atmosphere. In fact, if you consider the amount of carbon that's in the atmosphere and the ocean today, and you take this change in the C13 to C12 ratio, you can actually calculate how much fossil fuel carbon has accumulated in the atmosphere and in the upper ocean. So this is an important observation. It certainly confirms that the carbon that's accumulating in the atmosphere is coming from fossil fuels. And as I said, there are other ways that we can prove this that are even more direct. Okay, so CO2 levels are rising. They will continue to rise in the future. What we don't know for certain are the trajectories that carbon dioxide levels will take, simply because these forecasts are based on a number of factors. One would be probably the most important is economic growth or output. And the other, of course, is our transition to renewable energies. Energy efficiencies, improvements in energy efficiencies will also add some uncertainty. But what we can do is make projections with different assumptions about how those different variables will change. And I will show you several examples of those emission scenarios in a second. And then once you have some emission scenario for the amount of CO2 being added to the atmosphere, the question is how will global temperature respond to each of those emission scenarios? And that's a very complicated, challenging question to answer. We're using the most advanced numerical models in the world to try to simulate the climate under each scenario. And as I'll point out a little bit later, that's not trivial. There are some uncertainties, and I'll get into some of those in a moment. But let's get back to this question of how carbon dioxide levels will change into the future. Okay, so let's spend a few minutes on this graph. And what you have on this axis is the concentration of CO2 in the atmosphere, ranging from 200 to about 1250 ppm. And then time here, starting in 2000, going out to the year 2100. So a 100-year window. We're here now at 2020. Pre-industrial CO2 concentrations were around 280. By 2000, we were already at 350 ppm. And today, we're almost 420 ppm CO2. And then you see these various projections out into the future, the next 80 years or so. Now, as you can imagine, each of these represents some assumption about economic growth and the transition to renewables and away from fossil fuels. This is the most extreme scenario, the least optimistic, and this is a very optimistic scenario. These numbers are these acronyms, RCP, that is essentially called the representative concentration pathway. You don't have to remember that. 8.5, the number simply represents the amount of warming per unit square meter of surface of the planet that we will get from that rise in CO2 by the year 2100. So 8.5 watts per meter square in the most extreme scenario, 6, 4.5, and 2.6 watts per meter square. Those numbers may not mean much to you unless you think about the Earth's radiative balance. We receive something like 1,360 watts per meter square from the sun, at least at the top of the atmosphere. And so based on these emission scenarios, we can go ahead and model the climate in response to each of these scenarios. Now, one thing I will point out is that in these two extreme scenarios, the very pessimistic, the less pessimistic scenario, CO2 levels will get up to something like 750 to 1250 ppm by the year 2100. We're talking about just 80 years from now. And I would say that this requires that we continue to burn coal at a very high rate, which I think is reversing. I don't think that's a realistic scenario, that we're starting to already wean ourselves off coal a bit, as I'll show in a moment. There's some hope that we might follow this scenario that takes us to only 560 ppm, and I'll explain why that's important a little bit later. So now we have these carbon emission scenarios, and we can take this information and put it into climate models that are effectively simulating the Earth's climate. And what this graph shows is how the mean global temperature of Earth would change over the same period from 1900 to 2100 in response to those 4 different carbon emission scenarios that I just showed you. And these estimates are based on an ensemble of climate models, the best climate models in the world, and then we essentially take sort of the average of those models. And that's what you're seeing here. These bars represent the range of predictions from the different climate models for each of these scenarios. And so you can see for this pessimistic scenario, the RCP 8.5 mean global temperature could rise by as much as, say, 4 degrees centigrade by the year 2100, which is a lot. And then in the most optimistic scenario, global temperature only rises by about 1 to 1.5 degrees centigrade. And so again, these are simulations by numerical models, and they're just representing how the mean global temperature would change. What else can we expect with global warming? I think a lot of you are well aware of what happens if we warm the planet by as much as these models are forecasting, starting with things like sea ice distribution in the Arctic. Sea ice has been diminishing in coverage. This image is from yesterday, and sea ice should be much more expanded by this time of the year in the Northern Hemisphere relative to the long-term averages. So we're seeing a loss of Arctic sea ice. Glaciers and ice sheets are melting. We can document this quite clearly now, and as a consequence of that, sea level is rising, okay? And sea level has actually risen by about 8 inches over the last century. Most of that rise has occurred over the last 40 years. So you can almost see this acceleration of global warming and the effects that it has on, say, the ice sheets. An important aspect of all of this is that as the ice melts, both the sea ice and the continental ice sheets, the reflectivity or the shininess of the planet starts to decrease. So there's a positive feedback in the sense that more of the sunlight that reaches the planet's surface gets absorbed and is not reflected back into space. And this is one of the important feedbacks that was included in models early on. There are other feedbacks that need to be considered that are less well understood, involving clouds and so forth. And this is all part of what makes modeling climates, future climates, somewhat of a challenge. Now, another aspect of change that we expect with a warming atmosphere and warming oceans is something called intensification of the hydrologic cycle. And what this is in theory is that as we warm the atmosphere, the amount of vapor that the atmosphere can hold starts to increase at a rate of about 7% for every 1 degree centigrade of warming. Now, the reason why this is important is because that water vapor, the conversion of liquid water to vapor water requires a lot of energy, and it produces something called latent heat. That water vapor has a lot of energy, and as it condenses back into a liquid, it releases the heat back in the atmosphere. And what this does is it increases the motions in the atmosphere. Adding energy to the atmosphere starts to affect the way the atmosphere convects and the large scale and small scale atmospheric circulation patterns. As a consequence of that, rather than the whole planet becoming sort of wetter, some regions actually become drier, where you typically have high evaporation now. That tends to become even stronger. And places that are typically wetter now will see even more rainfall. But it's not quite that simple. What's clear is that on very short time scales, seasonal and slightly longer, we can see swings back and forth as if the amplitude of variability in precipitation is starting to increase. And we start to see a higher frequency of extreme precipitation events and droughts. And so this is something that the models replicate. I can show you one example. Here is a simulation. Again, this is based on a number of numerical models, so sort of representing an average of these models. And it's a projection for the period between 2081 and 2100, a 20-year window. And it just shows that some regions are becoming wetter in the greens. Some regions are becoming drier. And typically these are areas that are becoming drier tend to be dry already. For California, what it could mean, and we're probably starting to see evidence of this already, is that we get wetter winters and then sort of drier spring, fall seasons. And that's something that should continue to manifest itself as CO2 levels continue to rise and the planet warms. The other aspect of precipitation that's important is simply the frequency of extreme precipitation events. Just about every place in the models, at least, the extreme precipitation events increase in frequency. So these high rainfall events, the ones that tend to cause flooding, at least in theory, and even in current observations, look like they're starting to increase. The hard part is just understanding, exactly where regionally. The details are not always well understood. Now for California, we've already been seeing, at least I think, the initial impacts of global warming in terms of these wet dry cycles. Everyone remembers 2017, the fires, Santa Barbara, just really spectacular, scary. But just remember that same year, we had extreme precipitation here in the Santa Cruz Mountains, the flooding, the landslides, and so forth was record-setting. And that was on the heels of a long-term drought. And again, this year, arguably, the fires, the Western wildfires, not just in California, a record year. And this, in some ways, is exactly what you would expect, that it's not just that it's getting drier, but it's wetter, the combination of the two. Having a short, wet winter and then a long, dry season is a perfect recipe for forest fires. You build up the fuel and then dry it out and fires. So, and then of course, in the news lately is simply this hurricane season. The North Atlantic hurricane season was record-setting. This is a map showing all the named systems, the tropical depressions, tropical systems, and hurricanes, a record number. And just this week, Iota, Category 5 hurricane, hits Nicaragua, Honduras. Second time in 2 weeks, a hurricane of this magnitude. And the other thing about these hurricanes, this one in particular, it's spun up very quickly from basically a tropical system to category 5 in a matter of days. And that is something that is a bit unusual. Why are we seeing so many hurricanes, and why might the frequency of hurricanes or the intensity of hurricanes change in the future? It simply has to do with the fact that the ocean is warming. Since 1969, the upper 100 meters of the ocean has warmed by 0.33 degrees centigrade. That might not seem like a lot, but it's huge when you think about the amount of water involved and the amount of energy that is required to warm that water by just a few tenths of a degree. And so that energy is what hurricanes draw upon to sustain themselves. And our expectation is that the frequency of hurricanes will increase, their intensity could be higher, and they could actually migrate into much higher latitudes because of the warmer waters that extend into the extratropical regions. Okay, so we expect intensification of the hydrologic cycle. Here's the forecast: shifts in the seasonal cycle, increased frequency of extreme droughts, heavy precipitation events, increasing frequency, duration of tropical, extratropical cyclones. All of these cause flooding and also stress in terms of drought and crop production. And then of course, sea level rise and coastal flooding, again, part of that forecast. Now, as I alluded to earlier, there are uncertainties in these forecasts. They have to do a lot with feedbacks in the climate system and whether these feedbacks are linear or nonlinear, if there are more clouds or less clouds, or if the height of clouds changes, for instance. That's an important feedback on the rate of global warming or the pattern of global warming. The question is, how do we test theory and climate theory and numerical models? One way is to simply wait for the climate to change, like we're conducting an experiment where we just keep pumping greenhouse gases into the atmosphere and wait and see if the climate models got the forecasts correct. Now, that's kind of dangerous. And so most climate modelers really want to know if their models represent this Earth's climate dynamics in reality. And so they've turned to geologists for information about climates of the past. We know that the Earth has been warmer and cooler, and these variations in climate have been gradual for the most part. There are a few exceptions. And so what we have are opportunities from the past, case studies essentially, to test the climate models. So climatologists have been trying to simulate the climates of different time periods in the past, based partly on information that geologists can glean from the rock record about those past climates. And ideally, they've been looking at periods when we think greenhouse gas concentrations were high and the Earth was warmer. Now, for those of us who work to reconstruct these past climates, we do this by proxy, and I'll explain at least one of those proxies in a moment. And we're trying to get information or parameters such as the ocean temperatures, the land temperatures of the past, what were the precipitation patterns like. And this requires information also about the distribution of the continents. We know that the continents are slowly moving with time. And of course, atmospheric carbon dioxide concentrations. As I mentioned before, we have ice cores that go back several 100,000 years that allow us to very accurately reconstruct carbon dioxide concentration in the past. Beyond that, it becomes really challenging. I won't have time to go into the details of how we do that. But I will say that at a very basic level, fundamental level, What we know about Earth history is preserved in rocks. Basically, the sediments that are being deposited on land, in soils, in rivers, in lake bottoms, and coastal oceans, in the deep sea. These sediments tell us a lot about the environment at the time they were deposited. We can tell the difference between sediments that were deposited in a stream with low energy versus high energy, or we can tell whether sediments have been deposited in an ocean that's warm or cold, and so forth. And so there are very obvious aspects of the properties of these sediments that a first or second year undergraduate geology major could immediately look at and tell you something about the conditions under which these sediments were deposited. But over the last 30 or 40 years or so, we've also developed other techniques, for instance, based on the chemical composition of fossils that are preserved in these sediments, that can tell us something about the temperature of the water in which those fossils may have lived, as well as things like the carbon dioxide concentration of the atmosphere. And so it's the development of these tools, almost like in forensics, that have enabled us to reconstruct variations in Earth climate in unprecedented detail and precision. And that's what I'm going to talk about for the remainder of this evening's presentation. Now, in terms of the quality of the sediment archive of Earth history, the best place to go is the deep ocean. And the reason why is because the sediments are accumulating on the seafloor in layers year after year after year. And those layers are like pages of a history book. As you go deeper into the sediments, you're going further back in time. And the pages accumulate constantly. Unlike sediments on land where sedimentation can get disrupted, we have a much more continuous record of Earth history in these deep sea sediments. To retrieve those is not simple. We have to use large drilling ships, scientific drilling ships. This is the Resolution. It's basically being leased by what's known as the Ocean Drilling Program, previously the Deep Sea Drilling Project, and more recently the International Ocean Discovery Program. But it's a consortium of international countries that have invested in using this tool to recover, among other things, these sedimentary archives on the seafloor. Now, in most of the deep sea, what you're looking at in those cores is effectively mud, a white mud, and that mud itself has a high concentration of microfossils, plankton shells for the most part. These are zooplankton that effectively produce shells made of calcite, mostly. And it's those shells that allow us to determine the physical and chemical conditions of the ocean at the time that the shells were reproduced. And one of the most common methods that we've been using to get at past ocean temperatures is to measure the ratio of O18 to O16 in these calcite shells. So we refer to this as a proxy or a paleothermometer of temperature, and involves simply measuring the ratio of O18 to O16 that is in the calcium carbonate shell of these calcifiers. And we know from theory that the relative partitioning of the heavier to lighter isotope from seawater into the shell will change as a function of temperature. Again, because this has to do a lot with the energetics of the bonds that are being formed as calcium carbonate is forming. And we can prove the theory with experimental and field data. And so what you're looking at here in this graph is temperature on this axis, going from 5 to 30 degrees centigrade. And then the ratio of O18 to O16 in various shells. Some of these are from laboratory cultures, others are from field collections. And you can see that there's a very, very clear, not quite linear relationship between the ratio of O18 to O16 and temperature. So if we get a fossil shell like this and measure the O18 to O16 ratio and get a value of say -1 for that shell, I simply take that value to this graph and come across, and it gives us a temperature of roughly say 19 degrees centigrade, plus or minus 1 or 2 degrees with uncertainty. And that shell could be 55 million years old. And yet I would know the temperature of the seawater fairly precisely. We can do this with planktonic organisms that live in the surface ocean, as well as benthic organisms that live on the seafloor. So we get a temperature for the surface ocean as well as the bottom of the ocean. Okay, so we've drilled many, many sites in the ocean basins. We started drilling in the 1970s. The programs started to expand. The technology improved. We started to get better quality sediment cores from around the ocean. And what I'm going to show you is a compilation or splice of oxygen isotope-based estimates of ocean temperature from all these sites, mainly in the Atlantic and Pacific Ocean. And this is from a publication that came out in Science several weeks ago. And I'm going to spend some time on this figure. There's a lot here to digest. First of all, what you have here in this upper graph is temperature, or the temperature anomaly, relative to, say, the baseline, what we call the pre-industrial baseline, starting prior to the rise in CO2 in 1860 or so. And so that goes from 0 to about 16 degrees centigrade. And then time is on this axis, and it's not a linear axis. We have the last 20,000 years stretched out here, and then from say that period back about 500,000 years or so, 500,000 years. And then from this point forward, it goes back 5 million years, and then finally back 65 million years. And so as you can see, the temperature of the ocean has been colder, and this is during the last glacial maximum, which we know quite well. And then you can see the last interglacial, and then these repeated cycles of glacial interglacial cycles going back over at least 500,000 years, actually several million years. Now the scale becomes compressed, and so all this high frequency variability is now being compressed. And going back through time, you can see the Earth oceans getting warmer and warmer and warmer, back to a time known as the early Eocene or the early Eocene climatic optimum. This is one of the warmest periods of the last 90 million years, actually. And we knew that this was a warm period even before we started developing these sophisticated tools for reconstructing ocean temperatures. Geologists for many decades had observed fossils like crocodiles and palm trees in locations such as the Arctic, in rocks of this age. So there was always knowledge that this period was warmer. We just didn't know the details about the timing and how much warmer. And we know this quite well now. Now, in this bottom graph is the reconstruction of carbon dioxide over the same time period. And as I mentioned earlier, at least for the last 500,000 years, we have a very precise measure of CO2 simply because we're getting this from ice cores. The oldest ice on Antarctica goes back about 800,000 years or so. And so with those ice cores, we can get a very precise measurement, almost a direct measurement of the atmospheric CO2 concentration. And you can see they've been relatively low and co-varying with the glacial and interglacial cycles. Now, beyond that time, we're using a variety of other different proxies to get at the CO2 concentration. They're not as precise, but by using multiple proxies, we can get at least some estimate of the uncertainties and range. And basically what you see is that CO2 levels have generally been higher during this period when it's warmer, especially during the early Eocene climatic optimum. The CO2 levels were relatively high, on the order of about 1,500, we think, to 2,000 ppm. Now, there's one other part of this graph that you need to see, which is the projection out to the future, all right? Below are those CO2 projections, the RCP projections that I had mentioned earlier. In red is the RCP 8.5 out to 2300. And then you have 2.6 as the optimistic scenario here. So going out just to the year 2300. And then back on this panel, what you are looking at are the climate model estimates of the changes in mean global temperature following those different scenarios. Again, the very optimistic scenario, 2.6, and then the pessimistic scenario, RCP 8.5. And what should stand out is that the change in mean global temperature under that scenario by the year 2300 would be as high as we've seen on this planet, not for some 50 million years or so, when CO2 levels were about that high. And so almost immediately, with this type of reconstruction of climate over the last 66 million years, you can see that there is this correlation between carbon dioxide levels and the mean global temperature, okay? So that's an important result, and it's one step toward confirming greenhouse climate theory, okay? And it's important in part because it's also a way that we can kind of assess the sensitivity of the climate system to greenhouse forcing. If we look at the early Eocene and just a distribution of the surface temperatures, again, this is an anomaly relative to present day. So for any location, this just says that it's 2 or 4 or 6 degrees warmer than the temperature at that present day location. Obviously, in the early Eocene, with the mean global temperature being something like 12 to 14 degrees higher, the surface temperatures are much warmer, especially in the polar regions. You see what is known as polar amplification, greater warming at the poles. This has partly to do with ice albedo feedbacks. The loss of ice causes additional warming in those regions. And running out to the future, just going out to the year 2100, so over the next 80 years, again, following the 8.5 scenario, this is a projection of what the sea surface temperatures might look like. Everywhere is warmer by at least 2 degrees. In some cases, we see amplification temperatures regionally 4 or 6 degrees warmer, again, toward the Arctic, these high latitude regions where you're getting this sort of ice feedback. Okay, now here's another projection, which is sort of interesting, of how the land climate will change following the 8.5 scenario as we march forward through time toward higher and higher CO2 levels. It's at the year 2270, 2280, so almost to the year 2300. And what these colors represent are effectively an indication of what the climate would be like relative to the past. What would be the best analog of past climates for the climate in a particular region based on the models. And what you can see is that over large parts of the world, the Eocene, 40 to 50 million years ago, best represents the type of climate we might expect to see if CO2 levels get this high by the year 2300. And that is something to think about. It's really, again, impressive, but scary. Okay. Now, that's the evolution of the long-term climate trends. And in detail, we have a much better idea of how the climate's varying, in part because the resolution, the temporal resolution of the records have significantly improved over the last 2 decades. And that work is what's being represented in this reconstruction, the work of a large number of geoscientists. And what this also allows us to do is to pick out the high frequency variability. Some of that's related to variations in Earth's orbit. These are known as the Milankovitch cycles, very well known. But we also see anomalies in climate, short-lived anomalies. And one of the most impressive ones occurred 56 million years ago at the boundary between the Paleocene and Eocene epochs. We refer to it as the Pale-Eocene thermal maximum. You can see this short-lived spike in the mean global temperature. I can also tell you, and it's not represented in this graph, that the carbon dioxide levels also spiked during the same period. So the Paleocene thermal maximum, the PETM, it's a rapid and extreme global warming event, about 5 degrees of warming. The tropics got very hot, something like 40 degrees centigrade or close to 100 degrees Fahrenheit. The poles were very warm, over 20 degrees centigrade. We know that there was a massive release of carbon on the order of 5,000 gigatons of carbon over several thousand years. We think it was released by volcanism or somehow triggered by volcanism. This is still something that's being investigated and debated. But along with that global warming, what we have found is that global precipitation patterns and intensity change. The hydrologic cycle basically went into another mode. And along with that, we see perturbations to global biota and ecosystems. So what I'm going to focus on, of course, is this aspect of the Paleocene Eocene thermal maximum, the changes in precipitation patterns. And I forgot, I have this one slide. If you want to know what the Arctic looks like at 56 million years ago, based on our estimates of temperatures and fossils, it looks something like this compared to the present day Arctic. Okay, so at this point, I want to take you back in time, not geologic time, but in my time, or at least in the history of earth sciences, to the time when we discovered the PETM. We've only known about this event since 1991. I say only because I was a graduate student or studying a postdoc at the time. And it was this paper that was published in Nature by colleagues who at the time were at UC Santa Barbara, Jim Kennett and Lowell Stott. Lowell is now at USC. And this was an important paper describing this abrupt global warming event at the end of the Paleocene. It's based on measurements of oxygen isotopes in these calcareous fossils from a sediment core that was taken off of Antarctica. And so it showed this really distinct, very abrupt 4 or 5 degree warming. And along with that, in the ratio of carbon isotopes in the same shells, we see evidence of this negative excursion, as if the carbon cycle, just like the modern carbon cycle, was being perturbed by the sudden release of isotopically depleted carbon. And this is part of how we've been able to estimate how much carbon was released. The other effect of this massive carbon release was ocean acidification. And we've been able to quantify that ocean acidification in a way that also allows us to constrain how much carbon was released. And that's a whole nother story I can't get into. Now, what's interesting, and this is where I come in with some colleagues, is around the time that this paper was being published, I was starting a postdoctoral fellowship at the University of Michigan. And I'd gotten this paper to review, the one that I just showed you. And I read it and I was amazed by it. And what had happened is that I had run into a former graduate student from the University of Michigan, Paul Koch, who's now the Dean of PB Sci here at UC Santa Cruz. And we were talking about this paper and the possibility of trying to identify this time interval, this period of extreme global warming in the Bighorn Basin in Wyoming. And what we were able to do with the help of a vertebrate paleontologist, Phil Gingrich, is to collect fossils and work out the stratigraphic relationships of these sediments. Now, these sediments that you're looking at here in the Bighorn Basin represent paleosols. These are deposited in floodplains across a wide basin with rivers, meandering rivers running across that basin. And these sediments accumulate over time, and they give us a history of the evolution of that basin. We have also, within those sediments, fossils. These are fossil teeth of mammals. In fact, a lot of what we know about the evolution of land mammals during this period is based on fossils that have been extracted from this basin. And as you could see from this figure, which shows the radiation of different orders of land mammals, is that there's a major radiation event or speciation event that occurs right at the end of the Paleocene. So we collected samples, Paul Koch and myself, and eventually we were able to work out the stratigraphic relationships and correlate the marine record or the continental records with the changes that are occurring in the ocean and identify the Paleocene-Eocene boundary, or the PETM. As it turns out, it occurs right at this level. And what's important about this level in the Bighorn Basin is that if you look more closely, what occurs there, and this didn't really strike me at the time, at least the significance of it, is that there are massive sandstone deposits. And what these sandstones represent, if you look at them more closely, are channel deposits of rivers that suddenly became much more energetic and that were depositing or eroding lots of sand and redepositing this sand. And so essentially what happened during the onset of the PETM in the Bighorn Basin is at the end, the rivers went from meandering, slowly moving, slow velocity rivers to these braided high energy episodic type of river systems, moving lots of sand, as if the frequency of precipitation or high precipitation events started to increase. And this was a bit confusing, but it came into more clarity later when paleobotanists started to identify fossil leaves from these same sections. And what they noticed is that the flora of the PETM, at the onset of the PETM, indicated drying relative to the previous climate conditions. And so in the Bighorn Basin, it went from relatively warm and wet to hot and dry at the onset of the PETM. Now, across the Atlantic in the Pyrenees, other geologists working on similar sorts of terrestrial sections also found evidence of changes in stream energy in the Pyrenees. There's this conglomerate layer in the Pyrenees. A conglomerate is a real assortment of large and small stones. And what these typically reflect is a shift toward very high energy systems that are transporting large class in addition to smaller class. And so we have evidence from Europe of a change in the character of stream flow and energy during this period. Now I can see that I'm starting to run low on time. And I just want to point out that with these climate models, we've been able to go ahead and simulate the changes in the hydrology of the planet during the PETM using the atmospheric CO2 concentrations that we have reconstructed from our proxy records. And working with my colleagues, Jeff Keel and Christine Shields, who were based at NCAR in Boulder, Colorado, running the most advanced climate models and simulating the changes in the precipitation patterns through the PETM and showing that some regions became drier, some regions became wetter, at least according to the models. And our observations from different parts of the world have supported to some extent the changes in the climate. I'm just showing you titles of publications that came out over the last decade or so, reporting evidence of changes in the precipitation patterns or intensity during the PETM. And there have been dozens of sites where we've seen these changes. And in some, there's even evidence of increases in episodic fire along with the changes in the hydrology, not unlike what we would anticipate for the future. So this in itself is a verification of climate theory, the role of global warming, the intensification of the hydrologic cycle. And what I will leave you with is a simulation taking a high resolution climate model. This is work by Keel and Shields. It's a simulation of what we call precipitable water in the atmosphere during the PETM, under the sort of atmospheric CO2 conditions that we would have expected or that we have reconstructed for that period. And what you might be able to see is the genesis of tropical cyclones, lots of them propagating out into the mid and higher latitudes in places where you typically don't see hurricanes today. And so this might explain some of the observations that we see in places like Europe and the Pyrenees of these evidence of massive flooding events, high energy flooding events during this global warming event. So I will conclude on that. There are many lessons that we can glean from past, one of which is simple, that greenhouse theory seems to be very sound. And certainly with a doubling of CO2, getting to 560 ppm, the fact that our models predict that the Earth's temperature will increase by about 2 degrees C seems to be consistent with our observations of the past. That sea level will rise by a few tens of centimeter or more, again, consistent with observations of the past. That wet-dry cycles become more pronounced, certainly consistent with the observations, the frequency of heavy precipitation events, and tropical storms. So I could go on and on. I don't really have time to do so. One thing I will add is that our reconstructions of the changes in the climate and carbon cycle through the PETM indicate that carbon dioxide levels will come down through natural processes. Rock weathering, the production and burial of organic carbon will naturally remove carbon from the atmosphere, okay? This is not a surprise. What is a surprise is it will take tens of thousands of years for these natural processes to remove carbon from the atmosphere. So during the PETM, and that will be true in the future. So I will stop there and I will go ahead and take and answer questions.
Okay, Jim, can you hear me?
I can hear you.
Okay, great.
Should I exit the show or should I leave a slide on or something?
You know, there were a lot of questions about this slide that you showed with the 018 record and the CO2, the long term record. If you
Right.
put that up there. So there's lots of questions. And I'd say I categorize them as kind of some technical and data interpretation questions. There's some questions about communicating. How do you communicate solutions and that sort of thing. There's some carbon climate feedback questions. There's some mitigation, adaptation, and solution questions. So there's sort of these general categories. There's lots of questions. So I'm going to try to combine some of them.
Sure.
Okay. So actually, let's just like there's this graph shows that the RCP 8.5 2100 projection and the 2300 projection shows CO2 being extremely high, right? Higher than anything in the past 65 million years.
Yes.
Yeah. So I think that there's some questions about, tipping points, how much climate change have we committed to? Obviously, our trajectory right now is the RCP 8.5. That's the kind of business as usual scenario, right? So I think there's like sort of questions about that. So what happens to that carbon on what time scale?
Yeah.
And how do we get out of this?
So here's the thing. So with the variations in carbon dioxide through the geologic pass, we know that the primary emissions of carbon to the Earth's atmosphere come from volcanic activity. And the current rate of carbon emissions from volcanism is around a half a gigaton of carbon per year. And compared to 12 gigatons of carbon from fossil fuel emissions. So it's almost 2 orders of magnitude higher rate of carbon emissions from burning fossil fuels. And that's part of the reason why the CO2 levels are rising so fast, is because we're just simply opening up the can and letting all the carbon out. And the processes that would normally naturally take up carbon, remove it from the atmosphere and return it to the rocks, into the sediments or the Earth's deeper crust, operate much more slowly. And so, yeah, the CO2 levels will simply rise very rapidly because of the rate. And getting to 2300 ppm, which is extreme, or I should say, let's say 2000 ppm, that scenario is the very pessimistic one, where we don't do anything, we continue to burn. It would require burning a lot of coal, okay? Now, having said that, that very pessimistic scenario, at least prior to, we'll say the last election, the previous election, I think people were beginning to believe that we are not going to follow that 8.5 scenario. And this has a lot to do with it, which is, this is US energy, coal versus renewables, starting way back in 1850. To 2019. This is our energy from coal, right? And it was starting to peak, we were burning more and more coal. And then it started to reverse. And the renewables, electric, solar, wind, hydro has been fairly constant, but basically started to rise to the point where the amount of energy that we're generating from renewables in 2019 exceeded the amount of energy from coal in the US, okay? And I would say 20 years ago, nobody thought that was possible, or very few people believed that could happen. And yet it happened, and it happened very quickly. And I think that is something that is surprising, but it had a lot to do with technology and investment in renewables. And all of a sudden, that 8.5 scenario, maybe we can take that off the board, right? That we can say, okay, we're not going to go along the same 0.5. That more likely we'll be on this trajectory, and if we're lucky, we'll be on this lower trajectory of CO2 emissions out in the future. So
What do you think you could say about the climate change that we're committed to already?
Yeah, so that's an important question. And we're committed to a certain amount of global warming. And in fact, the latest IPCC report will focus on that question of if we wanted the planet to only warm by 1.5 degrees, basically we would have to reduce emissions tomorrow. In other words, we'd have to reverse the emissions, and by the year 2050, we would have to get to negative carbon emissions to prevent the planet from warming by more than 1.5 degree. Now, if we just sort of had steady emissions, the planet will still warm. There's this inertia in the system. The ocean is warming more slowly than the atmosphere because it's steep and heat has to propagate downward. And so we're committed to a certain amount of warming already. And also that means a certain amount of melting of ice, ice sheets, and sea level rise, all right? And I think this is important to acknowledge. I think that's where, when we start to think about, the future and what we need to plan for, and you can think about it. Here's San Francisco Bay, and we have projections of what the sea level might be doing out year 2100. And we're looking at something on the order of tens of centimeters of sea level rise, probably as much as a half a meter, depending on how quickly the ice sheets melt. And there's still some uncertainty there about that, but the estimates keep increasing as we learn more and more about the dynamics of ice sheets, at least from what I can see. And so, given that we have some estimates of what sea level will be doing, say 80 years out into the future, and you have to build infrastructure that's going to last, say, 50 to 100 years, we need to be trusting the models, taking into account the uncertainties in those estimates, and using that to build out infrastructure that has to last 100 years. And so in cases where you have coastal flooding issues or river flood, these are steps that can be taken now. And it requires trust in the science, right? That the scientists, the best scientists in the world, are getting it right, and with some degree of uncertainty, and that we can use these models to begin to plan out. And there are other issues as well. We're talking about infrastructure. There are also issues with agriculture, and then even population instability. As the planet gets warmer, the tropics become less habitable, maybe to the point of being uninhabitable, especially if you can't grow food. And needless to say, that can lead to mass immigration. We're probably seeing the initial effects of this in some parts of the world already. So
I think that people in the audience are asking questions, they're thinking about this, and they're asking questions about some mitigation. Well, there are a couple of things. One is planning for this, and sort of the other is, mitigation strategies or carbon capture strategies. And so I'll just ask you a couple questions about that people sent in. So one of them is about the sort of the recognition that a lot of the effects of global warming are very local, right? They have to do with small scale changes in precipitation and aridity and seasonality and things like that. And so the question is modeling happening at the smaller, kind of more relevant scales for planning, and are these results being communicated and being used by local officials for things like planning water resources and things like that?
yeah, I think I think the answer to that is that that is in progress. So on a local scale, especially when you're dealing with the hydrologic cycle and trying to model that, because of the convective nature of the atmosphere and the scale of convection, the model resolution has to be really high. So the grids and the models have to get smaller and smaller, like on the order of a kilometer or a few kilometers by a few kilometers, but maybe even smaller than that, to represent some of the smaller scale convective activity in the atmosphere. And so there's been progress in doing that and pushing the models forward, improving the resolution. Also still updating the physics in the models, especially on that scale, what climate modelers refer to as the microphysics. And of course, the issue there is computational limitations. So as the resolution of the models increase, the computational time it takes to run, say, a year of model time or several years of model time just increases by leaps and bounds. And so there's been this trade-off with the evolution of supercomputers or computing power and the sophistication of the models, kind of iteratively both increasing. We're probably starting to level off on computational abilities. And so, but yeah, so the idea is that if you want to be able to simulate what the climate might look like in a local area of, say, the South Bay or Santa Cruz at the year 2050, 2100, the changes in precipitation patterns on an annual basis, the likely frequency of extreme precipitation events. The models are producing these on some scale, and that information is available now. The question is, depending on the scale that you're interested in, we may not quite have that resolution, or at least the confidence in what the model is saying about a particular location. And so I think there is, the goal is to get to a point where, yeah, I think communities can work with the modelers to at least get some sense of what they're going to be dealing with in terms of, say, flooding, sea level, and again, with some uncertainties, and then building out infrastructure. And it's always a case of what you're willing to spend, I suppose, with infrastructure. Do you prepare for the worst case scenario or the best case scenario? But what we do know is that, the cost of floods, for instance, over the last decade, it's been enormous, in terms of just the US, okay? Every hurricane, and yeah, for California, or I should say the whole West Coast, these atmospheric rivers, these types of things will become more prevalent in terms of producing these extreme precipitation events. And so, if we kind of know how they're going to change, we can kind of prepare for them. Part of it's just not building in certain places, right? Zoning some regions as flood regions. Those will have to be expanded in some areas. But yeah, I don't, I'm not a climate modeler, so I can't say specifically exactly the way that community has been interacting with the government, local government, or federal government. But there's certainly in California, 20 years ago, people, vintners, grape growers were getting worried about, where they should plant certain varietals, that wouldn't do well under extreme heat. And so they consulted with climate modelers and got a sense of what elevations they might want to plant new vines that take 5 to 10 years to mature, thinking in advance about global warming. So, it's doable, and certainly I think it's recommended if the goal is to not have to spend lots of money down the road needlessly, right? So
okay, there was I just, because we're going to run out of time soon, I just wanted to switch to, there was a number of different questions that actually had to do with the PETM, so the nature of the event. And so I'll just mention a few things that people are curious about. One is the time scale over which the event occurred, and then also what the evidence is for impacts on, on particularly on the biology or ecological impacts of that event.
Yeah, so the entire event from the onset to the recovery spans about 100,000 years, and maybe a little bit more than 100,000 years. The onset of it, at first, it looked very abrupt, like it could be occurring over centuries. We think it may have occurred over a few thousand years. And so the carbon emission rates, if something on the order of like 5,000 gigatons of carbon was released, say over 1,000 years, that's about 5 gigatons of carbon or so per year. Those are about the same rates as sort of anthropogenic carbon emissions. And I think that aspect of it is still being worked on, the exact amount of time represented by the onset and the rate of global warming. But it was relatively fast, certainly from the perspective of geologic time. As far as where all that carbon came from, well, we're not sure. There's lots of volcanic activity in the North Atlantic around that time. It's an unusual type of volcanic activity in that the magma was injected into the crust. And so it was cooking carbon that's in the crust, sediments. And so the emissions rates of carbon were probably much higher than normal volcanism. But with the amount of carbon that was released at the rate it was released, a lot of that carbon got absorbed by the ocean initially, just like anthropogenic carbon dioxide today is being absorbed by the ocean. And we know this for a variety of reasons. First and foremost is that most of the calcium carbonate on the seafloor prior to that time started to dissolve away. Massive dissolution of seafloor calcium carbonate. And that's just an indication that the CO2 is being absorbed by water and lowering the pH of the water. And that's happening today. The surface ocean is being acidified as it absorbs CO2. What we get to see with the PETM is sort of the full scale of the process from the beginning to the end. So CO2 being absorbed in the surface ocean and then being swept into the deep ocean with overturning circulation. And so the whole ocean becomes acidified. Then the recovery time from the point that the carbon emissions backed off to the point where sort of the ocean carbon chemistry recovers and CO2 levels come back to sort of pre-event levels is about 100,000 years. And that's just the natural sequestration of carbon through chemical weathering of rocks, silicate rocks, and dissolution of seafloor carbonates, but also maybe burial within organic carbon. And so as far as the biologic effects, the impacts, there's a mass extinction of benthic forams. So those calcifying microorganisms living on the seafloor. Yeah, the ocean pH got a little too low and made it hard for them to precipitate their shells. As far as planktonic calcifiers, we don't see much of a response, in part because we think the pH changes were relatively small because of the rate of carbon emissions. So there's some degree of ocean buffering so that the pH didn't drop by, say, 0.5 or 6, more like 0.3. And we've been able to verify that with new proxies of ocean pH, that the change in surface ocean pH was around 0.3. So the message there is that calcifiers can tolerate some degree of changes, variability in pH. 0.3 might be a limit for some calcifiers. Others might be more sensitive. And so, oh, and I should say the diversity of corals did drop significantly at the end of the Paleocene. We just don't know the precise timing of that relative to the onset of the PTM. But people are working on that now. So
there's a couple of questions about methane, and I'm going to try to link them because there were a couple of them. One has to do with whether or not methane played a major role in the warm event, the PTM, and then the second is more about a lot of questions about carbon capture, but one of them about methane and whether or not removing methane from the atmosphere now would have a significant effect. So kind of, just a kind of a methane question for both what happened in the PTM and then also what you think about the role of methane now in global warming.
Well, I'll talk about the PTM, which is, we think that in addition to, say, the volcanic CO2 that was being released, because of the degree of ocean warming, that methane from two sources, a simple one that I think everyone knows about, permafrost. So Antarctica would have been largely permafrost at the time. There were no large ice sheets. And given how much the oceans warmed in the atmosphere, it's likely that permafrost also decomposed and might have released methane to the atmosphere. There are also methane hydrates in the seafloor, mainly again in the polar regions, but you find them throughout, and they're stable at high pressure and cold temperatures. These are basically ice crystals that nucleate around methane in sediments where you have high levels of methane. But those hydrates can destabilize if the ocean temperature warms. And so based on our estimates of the change in ocean temperature from the onset of the PTM to its peak, we know that by the peak of the PTM, there's no place in the ocean where hydrates would have been stable. And whatever methane hydrate was stored in sediments would have also been released to the atmosphere. And we think that might have been like an accelerant, part of a positive feedback that accelerated the rate at which the PTM occurred. I think it was just volcanic carbon emissions. The onset would have been slower, but then you get these feedbacks, these positive feedbacks through the carbon cycle that could have accelerated the rate at which carbon was being released. And that's a very finite reservoir of carbon, maybe just a few hundred petagrams of additional carbon. But it's, of course, methane's a fairly potent greenhouse gas. And so I think in the future, yeah, it helps to try to reduce methane emissions. And then as far as carbon sequestration, there's a whole community of scientists and engineers that have been working on methods to extract CO2 from the atmosphere. And they're obviously identifying ways that this can be done. And the question with all of them always is, how do you scale it up to the level that it needs to be to remove, hundreds of petagrams of carbon from the atmosphere, and then the cost of doing that. And so I think there's some promising approaches involving grinding up rocks, silicate rocks, and using it almost as fertilizer in agricultural areas, and that accelerates a natural process of chemical weathering that absorbs CO2 from the atmosphere. But the scale of that would have to be huge, and it takes energy to grind up rocks, and so you have to account for that. There may be a day where we can generate enough energy from non-CO2 emitting sources, renewable energies, or maybe fusion will come online. At that point, we can seriously, I think, pursue these carbon capture storage ideas or scenarios. But again, it's going to be hugely expensive, and ultimately there are political barriers to enabling these sort of geoengineering, planetary scale geoengineering scenarios. And so from my perspective, our best hope right now is to reduce carbon emissions as fast as possible, and to prevent us from getting to higher CO2 levels, so we potentially cross some sort of unforeseen climatic threshold. And so, but yeah, and given, the politics of of late, I should say, sometimes it's hard to see how we could, even as a nation, agree on a policy for removing carbon.
Okay, well, I think we've run out of time. Thank you, Jim, for fielding lots and lots of questions. So I'm going to just turn it over to George for some closing remarks.
Thank you, Jim and Christina, for that fascinating discussion. And please all join us on December 8th for a special Kraw lecture as Chancellor Cynthia LaRive welcomes Professor Carol W. Greider, recipient of the 2009 Nobel Laureate in Medicine, to our faculty and to UC Santa Cruz. Good night, everyone.
Good night. Thank you.